In this question, you're being asked to use linear interpolation. So what you have is 20 payments of $100 and 20 payments of $200. And all these are happening quarterly, so once every 3 months. And then it's going to accumulate up to 9,000. And then we need to find the nominal rate of interest convertible quarterly. So what we need to find is the I with the bracket 4 on top. So once again, we draw a diagram. There are 10 years. And then in the first 5 years, so for the first 20 payments, so each year we have 4 payments, so there are 20 payments here, and there's another 20 payments here. The first 20 payments are going to start off at $100, and the final 20 payments are going to be $200. So all this is going to accumulate up to 9,000. So first of all, let us set an equation up for this. So 9,000 is equal to, so I'm going to break this up into a combination of two annuities. So instead of 100 and 200, I'm going to visualize this as being a combination of 100 on both sides plus an extra 100 only on this end of the timeline. So throughout the entire timeline, you're receiving $100 per 3 months, and that's going to last all the way up till time 10. And then from time 5 to time 10, we're going to get an extra 100 for each quarter, each 3 months. So both of these are going to add up to 200. So I'm just breaking up this annuity into a combination of two annuities so that we can apply the annuity formulas. So this treatment is kind of similar to what we saw in the last question. So breaking it up like this, we can divide it into two separate annuities. So this term over here encapsulates the payments all the way from start to finish. It's all 100. And then this term over here encapsulates the payment that only happens from time 5 to time 10. So once you combine this, it all accumulates up to 9,000. So with a bit of rearrangement, you'll see that this relationship holds, equal to 0. So we want to solve this equation and to find I, but as you know, this equation is very hard to solve. We can't do it by hand, we're going to have to use a computer. And since we don't have a computer, we're going to have to approximate this answer using linear interpolation. So I'm going to let f of I be equal to this expression. Now, we were given some numbers. We were given these accumulation symbols for 2% and 2.5%. So right now, as you see in this question, when I use I is the effective rate of interest for a period of 3 months. So you can imagine from time 1 to time 0 to time 1, I'm breaking this up into 4 parts. So you can imagine each one of this is a period of 3 months. And I is the interest for one of these periods. And if I want to find I4, all I have to do is just to take I and then multiply by 4. So that's the definition of nominal rate of interest. Because if you want to find the effective rate within 1 quarter, you just divide it by 4. So using this formula, if I find I and then multiply by 4, then I'll find this. So right now we'll focus on finding the effective rate first before we multiply by 4 and get back the nominal rate. So now moving back to this equation. So we have the figures given to us. So let's substitute it into this function over here. So for 2%, let's just substitute that in. We're going to get S42% plus S22% minus 90. And then if you plug everything into your calculator, you get negative 5.3006. And then if you do it for 2.5%, naturally you expect this to be larger, right? Because S increases as I increases. So if we plug in a larger I, this whole expression should be larger. And indeed that is true, because in the end you'll get 2.9473. So this is larger. So we get a negative number and a positive number. So you can imagine there being a graph. This is I, this is f of I. So at 2%, this is negative over here. So this is 0.02. And then at 0.025, the graph is up here. It's positive. So it's at so this point would be 2.9473. This point would be negative 5.3006. And the graph would look something like this. It's not exactly a straight line. It's going to be slightly curved. But since this interval is small enough, it's going to be close to a straight line. and then our answer is going to be here. So in order to find our answer, we're going to assume that this is a straight line, and then by applying the formula for the slope, we can determine what exactly is this I over here. So by applying the formula for the slope, we know that. So let's apply the formula for the slope from end to end first. So f of 0.025 minus f.0.02 divided by 0.025 minus 0.02. So this is the formula for the slope of this line segment over here. And then we know that we will get the same answer, assuming this is a straight line. We'll get the same answer by applying this formula, f of I. So we're measuring the slope based on these 2 points. So just now we used these 2 points, now we're using these 2 points. So f of I minus f of 0.02 divided by I minus 0.02. So these numbers we all know. So these we've just found. F of I, by definition, is equal to 0, because we want I to be the interest rate such that f of I is equal to 0. And then, so the only unknown here is this I over here. And by arranging this expression that we have, you're gonna find your I. And once you do a bit of rearranging, once you plug these numbers into this equation that we have here, you're gonna get I is equal to 0.02321. And then recall in the original question, we're trying to find the nominal rate per quarter. So we're going to take this answer and then multiply by 4, and then that's going to give you 0.09285. So this is your answer. And always keep in mind that what we just did here, linear interpolation, so I treated this line segment as a straight line. In fact, it is always slightly curved, but since this interval is small enough, I can assume this is a straight line. So this would be a good approximation, and the approximation is just going to get better if you use a smaller width, but that's the idea of this method.